enough time, we do 2 papers today, okay?
Okay, deal.
And if not, you just bought yourself a bit more time to prepare it for next week. How does that sound?
Yeah, I can do it today. No worries. So mine is already a very kind of a piece of cake for you. So it's gonna be a very easy one. So yeah, I can do it.
Cake and coffee sounds good to me.
Yeah.
Right.
Coffee is the tough one, which must be the Victor's paper, and cookie will be the sweetie end.
Nice. Well, that's fantastic. If you both could share the link to your papers in the chat, that would be greatly helpful. Sure. Welcome to everyone else who joined us on Zoom here and live over on YouTube as well, including our NASA engineer today.
Good morning.
Good morning. It's a lot of energy for a Monday morning that you have that. Right. Welcome to Neuriccino on this Monday morning, bright and early, 9:30. Oh, sorry. Just got distracted. It's very confusing when someone comes in and licks your feet in the morning.
You should say that it's not someone.
Yes, the dog. I just thought I closed the door on him. Right, we have 2 papers. One of them is shared in the chat already, waiting for the second one, and I'm going to push them over on YouTube as well. Fantastic. Right, the way it works is you present a paper that got you excited over the last week, or a historical paper. All is fine. Anything you read that got you excited. And you come and present the paper to us briefly in terms of what the idea was, what they did, and then we talk about it and give input to the best of our knowledge. And that's basically it. So with that, Victor, if you want to make a start, share your screen, full screen, please, so we can all nicely see it. And then you have a paper called Glial Place Cells for us.
It is a preprint of a very exciting paper that Michelle's pointing out to me, and that is really exciting, actually. So here is the paper. Can you see it well? It's okay for everyone? Perfect. So directly to the figure, because, I mean, who cares about the text? So, I mean, for the presentation here, now come on, Steffi. It's for the presentation. So
you know how long it takes us to write single sentences, right?
I do know. But for Neuriccino, we do like good pictures and images. So so to study exactly the role of glial cells in the brain, it's a role that has been evolving, at least that our understanding of has been evolving, and there has been a lot of evidences showing that there is calcium activities in the glial cells in the brain, and which is a calcium activity which is mirroring neural activity of the nearby cells. And there have been some debate about how this mirroring of the neuronal activity could or could not be used in the actual processing of the information in the brain. And so this article argues that it's not just mirroring, it's probably integrating information, and actually it makes new information arises and allows for, it's more than just the sum of its parts. Like the neuron and the glial cells both contribute to the information processing in their own way, and there is more information when you take into account both cell population than if you take into account only neural cell population. So this is the gist of the article. And now to the results. First, what they do is to take mice, I think, I don't remember, I think it's mice, and they put it on a sort of wheel to make them move, and they project, so the mouse view is a virtual space. So basically they are in a virtual reality on a wheel that simulates the fact that they are walking, and a screen that simulates the view that is in front of them. That allows them to do calcium imaging in vivo with a 2-photon microscope into their brain, because they are head fixed, but they can still move inside of the virtual space. So the brain cells have been genetically modified to express calcium reporting proteins like GCAM6. In this first experiment, it's only the glial cells that have been marked with this marker, with this reporter, and so they wanted to see if they could decode the spatial information from where the mouse think it is, if they can decode it only looking at the glial cells calcium activity. So this is what they did, and you can see in the, okay, do you see my mouse? All right, you can see in the figure, the E part of the figure, then the response, the calcium response from different astrocytes mirror the position of the mouse in the virtual space. And so they acquired, they took all the astrocytes that showed an activity that was corresponding to the position, and they plotted them here according to their order in which they activated, basically during the fact that the mouse was walking. And so it's not just one mouse and not one trial. It's several mice across several trials. So, but you can really see that there is information encoded in these glial cells about the position of the mouse. So for now, it's very interesting, but as I said before, it could be just mirroring neuronal activity. But it's nice. It's a very nice confirmation that it works. There is information about that in the activity, in the calcium activity of glial cells. One thing that is interesting to know and explore too is that glial cells are not like one big cell that whose activity is the same everywhere. Actually, there are subdomains inside of the cells. Like, for example, they separated between different ROI with cell body ROI at the center, like it's called a soma ROI, and then there are all the arms, the process, as they call them. I don't know, is it probably the term for them? I just don't know much about glial cells. So the arms are called the process here. So you've got the process ROIs, several process per glial cell. And actually, they do not have necessarily the same response to the same position inside of the virtual space. So even inside a specific glial cell, you might the different part of it might be reacting to different position in the virtual space. It is because the calcium activity is a very local. If I understand correctly, it's a very local inside of the cell and can be driven by probably the neuron processes, but differently across a different part of the glial cell. So that I thought it was very interesting, and one of the results here on the right part is that the further you are from the there's one point of reference, the further, the more different the response, the calcium response will be. But still, there is a plateau. It's not completely different if you move a bit further. So I think it's even they took it even inside the So they tried to see if the distance was relevant, but even considering distance between RI inside of the same cell. So basically, they just say we don't care if the cell, if the RI that we are studying is inside the same cell. We just care about the distance between the RI, and seems to be the way to interpret it. But then they wanted to check if they could actually predict the position of the mouse only using the glial cells information. So what they did is to use a machine learning algorithm. It's called an SVM. It's a very basic but quite powerful machine learning algorithm. And so they managed actually to predict, to determine, using only glial cells, to determine the position of the mouse in the virtual space. So they did several different granularity of RI, so big RI or smaller RI, and it worked all the time. So here on the right part, for different granularity, so you can see the increasing number of RIs here for different granularities. The prediction is on the y-axis, and the actual position of the mouse in the virtual space is on the x-axis. And you can see that there is a pretty good prediction of where the mouse is supposed to be at one specific point. I didn't exactly get what their what the measure was here exactly, because they say that it's the number of events, but I didn't quite dig into what exactly it was in the method. But at least we can see that the glial information we have can be used to predict where the mouse is. So it is really relevant information about the spatial position. So then they wanted to know what's the difference between the neural response and the glial response, because that's actually what we're really interested into. So they did the same before with the glial cells, but they also marked the neuron with a different reporter, fluorescent reporter. So and they measure the same thing. So here we have kind of the same kind of result we had before with the glial cells calcium activations here, and here we've got the neural cells activity, the calcium activity of the neural cells. And so we've got many more neurons than astrocytes, but still it is you can see that it's still possible to see, well, you see very well the position, the relation between the position of the mouse and the activity of the neuron. You can see it too, but not as clearly, but you can see it too in the astrocytes. One thing that they noticed is that the activity, the calcium, the calcium response field, meaning that the time during which the astrocyte was activated in the in the visual space was larger than the one that of the neurons. That seems to indicate that the neurons are more specific, have more of very specific information about the position than the astrocyte. But does that mean that most of the neurons most of the information is actually encoded in the neurons, and we've got a more smooth information in the astrocytes? Well, they redid the experiment with the SVM and managed to show first that yes, you can have a better prediction. In blue here, you've got the neural prediction. You get a better prediction of the position using the neuron than using the astrocytes. But, and this is very interesting, if you use both information from the astrocytes and the neuron, you got an even better information, which means that there is information encoded in the astrocyte that is missing from the neurons. And this is what they argue, is that there is a complementarity of information between what is encoded in the neurons and what is encoded in the astrocytes. And that this might arise because of the way the astrocyte integrates information from the neuron, and that would make new information arise, and that could be used to modulate or to complement the information in the neurons. But anyway, this is something that they wanted to show. They also said that they did an analysis of mutual information analysis that I'm not super confident to explain. So I just said that they did that, and they showed that there is more information, well, there is complementary information at a statistical level between the neuron and the astrocytes. So yeah, they argue that it's not just mirroring, there is additional information in the astrocytes. And I think that, so this is their conclusion. I think this is very interesting, but to me, when I read it, I thought that there might be an alternative hypothesis that could also explain it while keeping the precedents, the previous hypothesis that it was just mirroring, that glial cells were just mirroring the neurons. Is that when we do calcium imaging, we are not actually lighting up all the cells in the brain and in the field of view. It's just some of them, a portion of them that we are actually viewing. Because if it was all of them, we probably wouldn't see everything. Or maybe I'm wrong. Maybe because it's not exactly my area of expertise. So if I'm wrong, I'm sorry. But the thing is, if we are indeed not seeing all the cells, we actually have a sample of both astrocytes and a sample of neurons that are not correlated toward each other. So it's very possible that if we had all the cells, we could see that this is the same information. But because we've got a random sample of each, we just happen to have more information, partial information in one population and partial information in the other. And together, there is more information, but actually it's just because we don't have the full complete view of the encoding in the brain cells. So this is my critique. It doesn't mean that the results are wrong, but I would have loved to see this point discussed at least, and I didn't see it. And yeah, thank you.
Thank you, Victor. Great paper. Are there questions in the audience? Yes, Patrick.
Hey, thanks for presenting, Victor. Really
Hi.
Cool. I'm a little bit curious about whether or not the prediction accuracy in support vector machine doesn't actually scale with the number of concordant input information, because I could imagine also that, but I'm not so sure if it's true, because then you wouldn't expect that you have complementary information or some different variants explained by astrocytes and neurons, but more or less more of the same, which is beneficial for the classifier. What do you think?
I think it's a fair point that you're raising, but this is also why they did the statistical analysis about the mutual information between the neural and glial activity. And so this is also something that I cannot really discuss because I'm not really, I cannot explain it and I'm not an expert in it. So I'm sorry about that. But I think they had like a good idea of what they were doing for this. But it's true that the SVM is just, it's a good way to illustrate it. But maybe, as you said, that if you put more information, or if you put more more data in input, even if there is redundant information, it will give you a better prediction. So I don't really know for this. I'm sorry.
No worries. I didn't want to put you under the spotlight.
No, it's okay. It's okay.
I was just curious. So when you said they tested for mutual information, what exactly, probably just if you know in detail, what exactly did they do? Did they try like multiple linear regression? I see you kind of smiling. So if you don't know, it's fine.
I don't know. Sorry.
Sorry. No worries.
I can try to find it back, but I think it would be best to discuss it a bit later if you want, if we can find it and discuss it. But yeah, they quantitatively tested the hypothesis of pairwise level using mutual information analysis and using mutual information breakdown analysis of ROI pairs. This is what they do, but I don't know what it is.
Me neither. So nevertheless, really interesting paper. It really highlights like some things we always take for granted that we know, like glia cells are just some form of helping cells, but potentially we can get more information out of that. So really cool.
Yeah, I think it's really nice. It's a nice article, and I'd like to see more of them like this, because although the method is also quite interesting, they really put the effort into it.
If you want to see more like this, there's an easy way. You just present it more regularly.
Yeah, I could do that.
Just checking. Leah has a question for us.
Yeah.
I try to speak. I'm in the paper. They have referred to the Moser work. For there is the Moser. It's a couple in Norway that they had the Nobel Prize in 2014, and they discovered this grid in the internal cortex where activated.
I can't hear you well. Sorry.
Can you hear me?
I just muted Michelle. You should be fine now.
Can you hear me?
Yeah.
Can you? Okay. So the Moser work, where they had the Nobel Prize in 2014 for the activation in the internal cortex that mirrored the localization of, I think it's also an experiment with mouse, and it's kind of related of this work that you presented. I don't know if they refer to that.
Well, they are citing different papers saying that they are prior work on this field, obviously, and they saying that those work mostly show that it's a mirroring of neural activity rather than a complementary activity. But I didn't really dig into the different citations, because here they just say the citations are just with numbers, so I didn't check exactly which one was which and everything. That's a bit beyond what we do here for the Neuriccino. But
no, because it happened to me to participate to a speech of Moser, and it was really close, the work and related. So
okay. Yeah, because yeah, all right. Because I saw that there was just discussion about things that were different before, but yeah, didn't see exactly what you're talking about. Maybe I just missed it, but I can see like.
No worries.
Yeah, because
it was my connection between words.
Yeah, no, they're saying that in the classical scenario, it's mostly what, as I said, modulation activity and mirroring activity, which would not provide further information about the neural activity, but yeah, I'm sorry, I can't tell you about that.
No worries. It was my connection. So there is this number pad that I share in the chat box that I think it's related. Maybe Stephanie can explain better than me the connection, but yeah.
I can't explain it better, but I had the same thought before you shared it in the chat, what the link would be with the place cells that they described. But we can just go back and read it together and learn together from it.
Sure.
Other questions? Yes, Hervé.
Yeah. Thank you, Victor. It's a complete. It's a naive. No, it's a interested. It's an interesting question because I'm wondering if there is any impact of this concomitant not activity but complementary signal from the neurons and the astrocytes. If there is any impact on the fMRI board signal, or do you see a way we could use this kind of article results in the fMRI field?
Oh, that's an excellent question. I hadn't thought about that.
I don't know neither. So
no. But I think that since they need energy anyway to work these cells, these glial cells, and that the fact that they mirror the neural activity, actually they might very well and probably do participate to the bold signal that we see in fMRI. But then there is the question of, is it really important for fMRI study directly
maybe
to know
not
which population activates? I don't think so. Is it important to know for the sake of it? Yes, I do. I'd love to know exactly which population is more important in the bold signal activations. But also, yeah, I've got to not forget that the bold signal is like super slow, and even if the calcium signal here is quite slow too compared to the actual spikes, like the microsecond spikes of action potential of cells, of the neural cells, it's still much faster than anything that we get on fMRI. But yeah, that's an excellent question. I'd like to know.
So I did a rapid check, but very rapid. So it seems that the board is the signal from the astrocytes and neurons are both taken by the bold signal. But an interesting thing I saw is that it seems that the astrocytes have a slower signal. So the bold signal, the end of the bold signal seems to be more related to the astrocyte than the neuron. So maybe there is something somewhere in the middle. So
okay, that's cool.
But still,
Michelle also had a question.
Now there was a comment regarding like the relationship between the. Can I share my screen?
Oh sure, sorry.
Because I actually present that. I used to present that during my course in Padova. So, you know, like this is a mechanism at the neuronal level that we measuring with the bold, and it's like very complex, and there is a lot of exchange of ions, and this is what's going on with the astrocyte. And like this figure, although it's really complex, really highlight the binding that there is between the neuronal activity and the astrocyte and its relationship with the blood flow. I'm just gonna skip that part, which is explaining what optogenetic is. And using optogenetics, Takata et al. Have been able to selectively activate neurons or astrocytes in the area of in a given area in a mice brain, and they did fMRI at the same time. That's the interesting part. And so what you can see here, if I remember well, exactly, so you get like a stimulation in blue, which is a blue light that can either activate neurons or astrocyte, and this is a percentage of both signal change. So what you see is actually, if you simulate the neuron, you get a percentage of both signals that happen. If you stimulate the astrocyte in the absence of the activity of the neuron, you also have a percentage of both signal change. And this demonstrates that actually the information that we capture with fMRI when we're measuring the activity of the brain is not only neurons, it's also astrocyte, and it could be astrocyte alone. But what's interesting, it's coming later in the paper, is that if you block the activity of the astrocyte and you try to stimulate the neurons, then you don't have, if I remember well, a bold signal change.
Interesting.
But looking at that figure, isn't it the same when you, I'm assuming from what you explained for A and C, is that at the bottom two panels, so the first one is you block the astrocyte, you don't get the activation for the neuron, but then the one below, isn't that the inverse, where you block the neuron and you don't get the activation for the astrocyte?
No, that's those are like for deactivation. It's different. Like the lower part is studying deactivation. The upper part is studying activations.
So what happens if you block the neuron with the astrocyte then?
If you block the neuron and you have the astrocyte, you still have the percentage of both signal change. If you have the astrocyte plus the neuron, you also have the both signal change. If you have the neuron but not the astrocyte, you don't have, I don't have it on the slide, the percentage, like the increase in signal change in both.
Okay.
And stop share.
Any other questions? No, everyone happy? Great. Well, in that case, we finish slightly early today. And we have a paper next week from Merve on the interaction between cognitive reserve and age-moderated effects of lesion load in stroke. So we're looking forward to that one. And we wish you an exciting week in science. See you next Monday. Bye.
Bye-bye.